Hello. Okay. So we are live and okay. So we can start the stream. Uh, we had sol till O. Alright. So we'll go for P Q R. We'll see P. Before that, let me make a new file. So there is a tree with n vertices numbered 1 to n. For each I, okay, one thing, let me do it quickly. How do you do the break thing? Okay, I don't think it is doing anything. How do you make that break? What do you say? That will be back type of thing. Is it here? I don't think so. Okay. Let me make a break screen. As you can look at Carlotta till then. Okay, she looks pretty annoying. So here and here, add source, screen capture. Okay, so it's cancel. We'll remove it. We'll remove the properties. I think this. Okay, so we have the break screen. Yep. So yeah. Okay. So let me log into this so that my whiteboard is saved, because every day it gets you know refreshed, so I don't want that. Okay, we are back now. Yep. I hope you guys can hear me. Are you able to hear me? Yes, fine. Okay, so let's go. Let's go. Let's go. Here, independent set. So there is a tree with n vertices. Numbered from this is this. The ith edge connects x and y. Taro is allowed to paint each vertex in white or black. Here it is not allowed to paint two adjacent vertices both in black. Find the number of ways in which the vertices can be painted. Modulo 10 to the power 9 plus 7. Okay. So there's a problem in graph called what was it called? Graph coloring problem. What was it? Graph coloring. What is it called? What is it called? I don't know. Bipartite, yes, bipartite graph. Yeah. Bipartite graph. Uh, so basically, we need to divide the tree into two sets, and how many in how many ways we can divide it into two sets. We need to return that. What is the M? Okay, so we have n edges. We have n edges. So what I'm thinking right now is we have n vertex, right? We have n vertices and n minus 1 edges. So for each edge we have xi connecting to yi. So if we try to observe things, we can see that for each edge there is two possible cases, right? Either both of them are colored white, okay, either both of them are colored white, or one of them is colored black. Okay, so this is the so this is the okay. Now if we have edge, for example, if we have this, okay, we have this one is connected to 2 and 2 is connected to 3. Okay, so 1, 2 and 3. Here if we start from 1, we can see that it has only one edge. So for all of its edges we can try to run a like BFS. Yeah, I think so. We can run a BFS. Okay, we will run a BFS, and in that BFS we will either put it into this category or this category. Okay, so if we put it into this category, there is one way, and here there is two way. Okay, but also the or basically whichever one we choose will affect the neighbors of each of the vertex involved in this, right? So if we choose this as black, this cannot be black, so it has to be white, right? So similarly, if we choose this as white, then we will have the option of choosing this as white or black. So we have two options: choosing the current vertex and coloring it as white. In that case, we'll just go to the next vertex and do the same thing. Okay, number of ways to do that. And if we have colored it as black, then the next guy, the neighbor of it, can only be colored white, right? We cannot have two black consecutive. So I'm kind of trying to I'm trying to come up with a transition here. So you see, let's see for a better example. Okay, this example, we have 1 connected to 2, 3, and 4. Okay, so we have 1 connected to 2, 3, and 4. Now suppose we start from 1. Okay, we started from 1, then we can choose 1 as white. In that case all 3 can be white, right? Or all 3 can be black, or 2 of them can be black, or 1 of them can be black. So we have different possibilities. But if we choose this as black, then there is only one choice, to color them as white. You can see here this case. Okay, so if I choose white, you can see we have all the we have different options. We color all as white, we color 1 as black, 3 black, 2 black, 3 black, 4 black, we color 2 of them as black, or we color all of them black. So we have different options. Okay, so suppose our DP gives me, U is basically vertex, as our DP gives me the number of ways to color, number of ways to color, number of ways to color, ways to paint, the subtree. I don't think there is a subtree concept here, because we can have a subtree concept. Let's just go with that. 2, 3, 4. Okay, so number of ways to paint the subtree U. Okay, in that case, our DP U will be what? We have different cases, right? If we have a single node, if there is nothing below it, if there is nothing below it, just a second. Okay, so I don't think this is enough. We will do DP U C. What is C here? So number of ways to paint the subtree U if vertex U, if vertex U is painted C, something like this. So our DP UC will be, if I choose suppose there is no subtree below it, right? So in that case, how do we do it then? What? How will we go to the base case? If there is only one, if there is only one, we also need to check if we are not going in the parent's direction. So we'll have to look into that as well. Okay, so DPUC can be C can either be black or white, right? If we have colored this as black, if we have colored this as black, okay, if we have colored this as black, in that case, all the neighbors will be colored white. Okay. But if we have C as white, if we have C as white, then we have the option of doing this summation I dp vi white plus summation I dpvi black. Okay, so if C is white, I'm just hypothesizing right now because I don't know if it will work or not. Just trying to, the final step will be to try to come up with a test case where it fails, or we can try to implement it and see if it fails or not. Okay, so this is for the transition part, and for the base case also we need to check vi is not equal to parent of ui. Okay, we need to check this, and vi not equal to parent of ui. We are going downwards, we are going in the this direction. And what will be the base case? Suppose we cannot go, if we cannot go down, okay, if we cannot go down, then If we cannot go down, then we'll have to we'll have two options, right? Or depending on the parent that we have. This is what I'm thinking. We will have two options if parent is -1. Okay. Basically, if we have only one node in the entire tree, and we'll have one if if the if parent color is black, or here parent color is white. Also, in case we are not able to do this bipartition, then 0 if what color of vi is equal to color of parent. Somehow we found this thing. Okay, so how do I implement this? I've come up with a solution. I'm not sure if it is correct or not. These are all the base cases. This is the state, and the answer will be, of course, the answer will be in state transition and we have our answer in dp 1, and let's say we colored it black, plus dp1, let's say we colored it white. Okay, so the thing is, I'm thinking of doing a where is the I'm thinking of doing a recursive solution for this, and if I'm comfortable, I'll go for a the bottom up. Okay, so what is the time complexity for this solution? So for each vertex, we are doing at most 2 recursive calls, right? Or no, we are doing 3 recursive calls. So for n, we can go up to, and also this is not a single recursive call, but rather we will have the entire adjacent neighbors. We will call with all the neighbor elements, right? So it can go to, for each neighbor we will have all the neighbors and all the neighbors. So at max, how many neighbors can it have? This is a general tree, right? So can have n neighbors and can have n nodes. So n into n minus 1, n to the power n minus 1 ways, which is not feasible. Okay, so that was the recursive solution. And what are the constraints? Constraints are 10 to the power 5. Okay, the more I look at it, I'm not sure if our solution will work. And I'm not even sure what will be the root here. Can we just start from any? Yeah, we can start from any vertex, I think. So we'll start from 1. Okay, we will make 1 as the root. Then we'll have a parent in the recursive function, and that parent will be checked for okay, so our main function will be a boolean function, and we will check if it is possible to do it. If it is possible, then how will we update the it is not normal bipartite also, because there is a condition that we can have 2 white vertex but not 2 black vertex together or adjacent. So normal bipartite would be like this thing or this thing. So there are 2, but it is a modified bipartite. Okay, I'm not here for that. for this. Okay. Mm. So I was kind of right. है ना? Think I was kind of right. Yep. Okay. Root the tree at node 1, allowing us to define a subtree of each node. Let dp0 represent the number of ways the subtree can append such as the y pointer. Similarly, number of ways the subtree can append is black. Okay. The number of ways to paint a subtree that such that the root node is painted white is the product of the ways to paint the child subtrees. The number of ways to paint a child subtree is the sum of how to paint it white and how to paint it black. So the transition will be okay. Okay, so we have two cases similar to what I did, but the only mistake I did was I did this. It is not adding them because we need different ways, right? I think multiplication is so. Let's say we have a tree. Let's take this as an example. We have two options for this guy, either black or white. Two options here, black white. Two options here, black white. But I understand this one. Okay, but the okay is the sum of how to paint white. Product of the ways to paint the child subtrees. Why is it product? Is it because all of them these are linked together and causing change in one thing can have okay. So it is kind of like this, that if you have a tree like this and here we have a subtree, okay, a left subtree and we have a right subtree. So and we can do this legally or basically abiding the condition. We can have two ways to do it and we can have three ways to do it. Okay, so the total number of ways to do it will be 6, not 5. Why? Because if we choose the first option we can still have 3 here, and if I choose the second one we can still. So basically it is multiplication, not addition. So I was wrong on that front, but still anyway I think I was very close. I don't know about this though, the base case. I'm sure this is correct. This will be pi. This will also be pi. What is the base case? So number of ways to paint it is 1 in both the cases. Okay. So yes, we are doing a DFS, recursive solution only, and that DFS we have a DP, and we are setting DP state to 1. And so initially we have one way of painting that vertex in both the color. Okay, and for all the different uh, vertex of that particular vertex, we are checking if it is not parent. Basically, we don't want to go up again, so we are doing the DFS again, and we are uh, checking for this, coloring it as uh, white first. Okay, so we are coloring white first, and then we are doing the black. And I'm sure the DFS and DP is initialized as 0 here only. So for all the states it is initialized as 0 first. Okay. So when we start with 0, it will be set to 1. Okay. And okay, and there is no way of see what I was thinking, that when I did this thing, no, not this thing, I was thinking of a bipartite graph, and in graph there is a possibility that we have a cycle, right? So suppose I updated this one, but it ended up violating the condition, because these two are now the same. Okay, we have this as black, this is white, and we did this as black, so this is not correct. So yeah, this is not a graph, it is a tree, so there is no cycle. So if it is as long as it is not a parent, then we can comfortably color it in black or white if it is white, or in white if it is black. I think that is the case here. Okay, let me write it. As long as we are tree, there is no possibility of coloring a node, coloring a child node same as the parent, as there is no cycles present. So basically if we had a cycle, then there might be a possibility that yes, we reach this node first, so we'll color it, and yeah, you can see. So in tree there is no such thing. Okay, so we'll solve it, and we need to do mod, right? Okay, mod. Okay, so we'll do this, let's just say this, and we have what we need adjacency as well. So vector I adjacency 10 to the power 5 n and dpn, and we need two color only. We'll take n as input, okay, and we need to do this. F I 0 and n minus 1. Sorry, we'll do int x y scene x y and adjacency x dot pb y adjacency y dot pb x. So this takes care of the part, input part. Now we have the graph, and we'll do DFS starting from 1. This is going to be a 1 indexed, and one parent of 1 is -1, and then we'll do dp coloring it as white, what is the total way of coloring the subtree belonging to 1 as white or black, or vice versa, and this will be our answer. Okay, so we have void DFS. It will start from source and parent. Okay, and dp of our source and 0 will be 1 initially, and dp of source 1 will also be 1, and for all the neighbors in its vicinity, we'll just check is if it is not equal to parent. Okay, and then we'll run a loop again, run the DFS again, and now this time it will be node and parent is src, and again while we do this, after the DFS is done, we'll update the DP state. This case is for let's say coloring the current vertex as white. Two options for the subtree, either black or white. Just so it will be dp of source, and the color is, of course, we have colored it as white, right? So let's say white is 1 and black is 0. So it will be equal to dp of source 1 multiplied by dp of node 0. Plus dp of node 1. So we do this and we do this mod, and also we do a mod here, and again we if have a source we have already done the TFS, right? Okay, so we don't need to do the TFS again. We'll just update it. 0 is source 0 multiplied by, we can only color it in white now, so it will be node and white, and we will mod it. I think this should work. Okay, let us see. Okay, dp was not declared. Why? dp is declared. Man, dp is declared 40. This is how you do array, right? Am I tripping out? Is this Java? No, this is how you do. Okay, sorry. The answer is 5. I'm not sure if it is the correct answer. Okay, it is the correct answer. So for this, so it's 9. Yep. So I think I was this time for this tree question I was very close, like 85% close to the correct answer, and I think I would have got it if like I've tried to implement it, but I was not sure how to implement this. I think it worked out fine. Okay, this is wrong. This thing is wrong. So maybe multiplied by 3. 50 times 3, 150. Ah, because of this. Sorry. And then we'll do DFS from 1 or 0, it doesn't matter. If we do it from here, we'll do it from here and here. Okay. It works. It works. We'll copy it and we'll paste it. Verify, please verify. Succeed. Submit. TLE, MLE, wrong answer. TLE, MLE, wrong answer. Okay, fuck, wrong answer. Okay. Okay. Sorry. This thing. I forgot to do that equal sign. Okay, correct. Let's move forward with the flowers. There are n flowers arranged in a row. For each I, the height and the beauty of the ith flower from the left is hi and ai, respectively. Here h1, h2, hn are all distinct. Taro is pulling out some flowers so that the following condition is met. Taro is pulling out some flowers so that the following condition is met. The heights of the remaining flowers are monotonically increasing from left to right. Okay. The fact that it is 10 to the 2 and number 5. So if we select one, then we will need to check in log n time if it is monotonically increasing or not. Or we can do the opposite. We'll choose in log n time and then do it. So there are different ways, and I think I am done for the day. Okay. Am I audible now? Okay, so what I was saying is I will not be able to stream tomorrow and the day after because I have a meeting and I have a training and I will be very late in reaching home. So yeah. So I'll try to do the makeup stream on the weekends. That is I can do. So yeah. So we'll not be able to stream for the 2 days, and whoever is watching, I hope you utilize these 2 days, unlike me. And yeah. Uh, with that, I hope that you have a good night and peace.